Good morning, AP Kim. Welcome back, and welcome to my kitchen too. It's nice to see you again. Happy St. Patrick's Day. Sorry for my late start. I got my diet due now. I'm ready to go. I hope you got one too, and you're ready to go too. Right. So today we're going to move on to the next section, which is how exactly do you determine those orders of reactants? How do you determine those exponents up there? We've already seen how they affect the rate of the reaction, but how do you figure them out in the first place? Well, there's two ways to do that. The first way we'll talk about today. The second one we'll talk about next time. Right. So first, let's look at reaction. This is the same reaction we saw the other day in class, the one that kind of looked like bad apple juice or very bad urine sample. We were reducing iron to Fe2+, in the process oxidizing iodide into iodine, causing the dark color. And so using our colorimeter, we followed the rate of the reaction, and this corresponds to the concentration of our reactant over time, and thus the rate of the reaction. We can figure out the rate of the reaction by finding the slope of the curve. And we're going to look at the very beginning here, and it has a slope of about 0.82. Right? You physics people should be familiar with the idea of slope as being equal to a speed or a rate. Okay? If not, that's okay, just go with it. Right? And so what we're going to do to figure out how the reaction rate is affected by the concentrations, we're going to change the concentration, but we're going to do it in a very controlled manner using controls and variables. We had two reactants. We're going to keep one the same and change the other one so that if the rate changes, we know exactly why it changed. And by knowing how much the rate changed, then we can figure out what that exponent is, what that order is. Right? And so let me go ahead and change the rate. This is some old data I had lying around, so I can do it pretty easily. But I'm going to run it again, and this time I'm going to double the concentration of one of the reactants, and that's shown by the blue here. So I doubled the concentration, so that's why the solution would appear darker. But you can see that the curve looks pretty much the same. It's just shifted upward. So I'm going to find the slope of this line as well, and it looks to be very, very similar to our original slope. So what this tells me is I doubled the concentration of one of the reactants, and it did not affect the rate at all. Therefore, the rate law must not depend on the concentration of that reactant. What order would that be? That'd be zeroth order, right? No matter what you do to the concentration, anything raised to the zeroth power is still going to be 1, and so it has no effect on it, right? So once we know that, then we change the other reactant, see what effect it has. So let me do that now. I'm going to double the other reactant, the second reactant, and graph that. And this time, you see that again, it absorbed more because there's more stuff there. But this time you can see that the curve of the line is a little bit different. The slope is a little bit different. And so I'm just going to go ahead and figure out the slope of that line. And here we go. Okay. And it's about half of what it was before. And so what this tells me is that when I changed the concentration of the other reactant, I don't think I doubled it, I think I halved it, sorry. The slope also halved. And so if you do one thing to the concentration and the same thing happens to the rate, that means it's going to be a first order reaction. Okay? And so this is just one way that we can tell what the order is going to be. Now, will you have to do this yourself? Absolutely not. Usually, the problems give you the hard work for you. They do the hard work for you. And so let me see another example of this. So this is the note packet. I've attached it to this post, so if you don't have it on you, if you didn't pick it up, you can either follow along electronically or you can print one off, whatever works best for you. Okay. But let's look at example 1 first. And so example 1 has three first of all, you gotta look at the reaction, I guess. And so the reaction is A going to P. And so we're going to do this 3 times. We're going to change the concentration of A each time we do it. Really, you only have to do it twice, but we did it 3 just to be sure. Right? And so if you look at the concentration of A, in trial 1 to 2, we doubled the concentration of A. Okay? And then you look and see, well, what did that do to the rate? And you can either figure it out in your head or you can divide the two. But when we doubled the concentration of A, we doubled the rate. And so anytime you do one thing to the concentration and the same thing happens to the rate, that means it's first order. Okay? And so then we automatically know that in our rate law, A is going to have an exponent of 1 for the first order. Right? So we can write our rate law then as rate equals K times A to the first. The 1 is optional, of course, you don't need it. Right? Not bad, eh? Pretty simple, huh? Just using your old noggin. And then, once we know what order it is, then we can figure out what the value of the rate constant is. And for this, you can choose any trial you want to, and you just plug and chug. So I used trial 1. I plugged in the concentration of A that was given to us, of 0.35. I plugged in the rate for trial 1, and then I solved for K, got the value of 0.0021. If you want to work with units, again, it's not a big deal. They don't ask about it very often, but if you want to work with units, I showed how you can do that off to the side. Basically, instead of using numbers, you use units instead. And so the rate's in units of moles per liter seconds. So I have that on the rate side. And I have K, and then the concentration, I guess, is in moles per liter. So moles cancel out, liters cancel out, and I'm left with K equals 1 over seconds. And so the full answer would be 0.0021 1 over seconds. As far as I'm concerned, all you're going to need is 0.0021. That's good enough for me. Okay. All right. So you guys can try the next one. I gotta let my dog out, and then I'll be right back, and you can see how you did. Okay, we're back. This time we are decomposing NOCL into NO and Cl2. This time they gave us a whole bunch of trials. This is really going above and beyond here. Again, we only need 2 in this case. They give us 4. So you can choose any 2 trials you want to. Doesn't matter. I chose 2 and 3 because they were small and it was a nice change. It just doubled. Okay. And so going from trial 3 to trial 2, we doubled the amount of NOCL, and then we look over here and see what the rate did. If you can do math in your head, swell. If not, I had to divide the 2. And so when I doubled NOCL, I actually increased the rate by 4 times. 4 times, right? And so we doubled the rate, we doubled the concentration, we quadrupled the rate, and so that tells us that it's going to be second order, because 2 squared is 4, right? And so our reaction is second order in NOCL, and so we can write a rate law as rate equals K times NOCL squared. And then everything else is similar. You can find the rate constant K. I used trial 1. I plugged in the rate. I plugged in the amount of NOCL that was given to us. Don't forget the square, and solve for a value of 0.66. Again, if you wanted to, you could use units. I'm not too concerned about that at this point. The next part is just let me scooch myself up here. The next part is just a reminder of the stoichiometry of things. If you notice in the table, it tells you the rate in terms of NOCL that was used up, decomposed. Okay? That's what they defined up here. If you wanted to, you could define the rate of the reaction in terms of the NO that was formed or the Cl2 that was formed, since they're products. And to do that, it's just stoichiometry. For every 2 NOCL that you use, you're going to make 2 NO, and so that's summarized right there in the little ratio. And so the rate of trial 1 in terms of NOCL, and multiply by 2 over 2 to get the same rate for NO. For Cl2, if you notice, we only make half as much Cl2 as we use NOCL, and so I have a 1 to 2 ratio here, just like in stoic, and I get 0.0299. Okay, so those were some simple examples. Hopefully they're almost kind of fun. It's kind of like a problem to solve. Let's go flip to the next page where we have two reactants instead. In Charlotte, I did this just for you. 2 colors. Mine don't look quite as nice as yours, but yeah, it's all I had handy. Okay, so in this case we have A plus B going to P. So this is kind of like the example we saw in the very beginning on Logger Pro. So we have 2 reactants to work with, and we have a lot of data. And so what we're going to do is just, we're going to look for 2 trials. Sorry, my cat's going psycho over there. We're going to look for 2 trials that have the same amount of A but different amounts of B. Then we're going to compare the rates. And then we'll look for 2 trials that have the same B and different A's and compare those rates. Okay? Let's see, so I have a lot going on here. Let me go over here to the blue here. So in trials 1 and 2, we kept A the same and we tripled the amount of B. Right? So this is a good pair of trials to figure out what effect B has on the rate. Right? So I described that down here in the blue. And so we held A constant, we tripled B, and then we look and see what the rate did. And if you notice, the rate tripled. And so anytime you do one thing to the concentrations and the same thing happens to the rate, then it's going to be first order. So we tripled the amount of B we had, the rate tripled, and so B is first order. Halfway done. Next task is to figure out what effect A has on the reaction. And so we find two trials that have the same B. Let's see, it looks like 1 and 3 would be the best shot there. And then we look for differing A and 1 and 3. Okay. So we're doubling the amount of A, going from 1 to 3. We're keeping B the same. So if the rate changes, it's because of A. Okay. And so that's over here in the red. We doubled the amount of A, and that made the rate go up by 4 times. Again, just comparing the two rates in trials 1 and 3. And so again, anytime you change the concentration and the rate does the square of it, then that's going to be second order. Right? And so boom, we have it second order in A, and so now we're ready to write a whole rate law as the rate equals K times A squared, right there, times B to the first. Okay. So a little bit more work, twice as much I guess, but still same idea. Hopefully not too difficult. We can find the rate constant then. We can use any trial we want to. Just plug in chug. Using trial 1, we plug in the rate from 1, the amount of A squared, amount of B, and we get a value of 0.15. Okay. So that's just one way to do it. You can choose a lot of different trials if you wanted to, but you should end up with the same answer. Okay. All right, you guys can try example 4, and then we'll see how you did. Okay, for example 4, this time we've got iodide, and it's been a while. I don't remember what that thing is called. The S2O82-, we'll say that, and we're reacting them. And so let's see, in the blue here, I'm looking for two trials that have the same amount of S2O8 but different amounts of I-. And then we're going to see how I- affects the rate. Okay. And so again, that's down here in blue. Here it is down here in the corner. And so we double the amount of I-, okay, and going from 0.4 to 0.04 to 0.08, and the rate also doubled. Okay. And so therefore it's first order in I-. For S2O8, I look for two trials that have the same amount of I- but different amounts of S2O8. And so 1 and 3 looked like a good choice. And so I'm going to compare those two and just ignore the rest. And so here we double the amount of S2O8, and the rate has also doubled as well. Okay? And so that means it's first order. Okay? And so therefore we can write the overall rate law right up here as rate equals K times I- to the first times S2O8 2- to the first. Okay? Notice again that the orders of the reactions of the reactants have no relation to the coefficients in the overall balance equation. You have no idea what they are. You got to figure them out experimentally. And so then we can figure out what our rate constant is. So again, I just chose trial 1. I plugged and chugged the rate. The concentration is given, raised to the first power in this case, and figure out the K value. And now the beauty of this thing is that we can use this rate law to figure out anything for any reaction. We can figure out how fast a reaction will go if we know the concentrations. We can figure out what concentration we need to go a certain rate. We can figure out the rate constant. So it's quite handy to have in your pocket. And so in this last case here, we know the rate, but we don't know the initial amount of S2O8 that we started with. And so we can plug and chug and figure out what that is. And so I got a value of 0.03. Okay. And so that's about it. Again, the whole idea is just to use your controls and variables, try to keep one thing the same and change other things, see what effect that has on the rate, and that's about it. So I hope you liked it. Now you can go on and try the AP Online 19.2. Work through it as best you can. I'm sure you'll do fine. I will post some solutions, some answers to that too, and I think that's about it. So enjoy your day, and tomorrow we'll learn the second way to figure out what order your reaction is. Involves some graphs. All right, see you later. Bye.